Hello viewers, I Histogram welcome you to the second part of collection and classification of data, frequency distribution. In this script, we will study about the frequency distribution, various terms used in frequency distribution, the various kinds of frequency distributions, graphs of frequency distribution, and methods of constructing class intervals. Before proceeding to the study of various kinds of frequency distribution, we'll first acquaint ourselves with the terms which are going to be used in the discussion. When the values of variables is defined in successive classes and the number of observations corresponding to each class is treated as frequency of each class, the resulting distribution of classes and frequency is termed as frequency distribution. In other words, a mathematical function showing the number of instances in which a variable takes each of its possible values. In statistics, it is a table that displays the frequency of various outcomes in a sample. Each entry in the table contains the frequency or the count of occurrence of values within a particular group or interval, and in this way the table summarizes the distribution of values in the sample. Example 1. In a group of 10% with their ages varying from 25 to 44 years, a frequency distribution may be formed as follows, given in table 1.1. So table 1.1 gives us the age of classification of 10 persons. The above table gives a quick glance at the age group of all the persons in the group, where variable x is ranging from 21 to 44 years, which is depicted in an array of ascending order. That is, from the lowest value of the variable to the highest values, divided in the form of class intervals 21 to 24, 25 to 29, 30 to 34, 35 to 39, and 40 to 44. The class limits are 25, 23, 21, 30, 21, 34, 35, 39, 24, 40, and 44. The size of a class interval is 5. The first one, variable. A measurable quantity which can vary from one individual to another is called a variable. For example, prices, wages, rainfall records, etc. There are two types of variables: continuous variables. Quantities which can take any numerical value within a certain range are called continuous variables. For example, height of students in a school. Second one, discontinuous variable. Quantities which can take only discrete values are called as discontinuous variables. For example, number of petals in a flower. Now the second one, array. An array is an arrangement of variables in ascending or descending order of their magnitude. For example, if the marks of 5 students in the subject of physics are 25, 49, 30, 42, and 45, the array of ascending order will be 25, 30, 42, 45 and 49. And the array of descending order will be 49, 45, 42, 30 and 25. Now let's come to the third one, range. The difference between the largest and the smallest value is called the range of data. For example, considering the marks of the students given in the above paragraph, the range of marks of 5 students in the subject of physics is 49 minus 25, which is equal to 24. Fourth one, class frequency. Number of observations falling against a class is termed as frequency of that class. Fifth one, class intervals and class limits. A symbol defining a class, for example 25 to 29 in table 1.1, is called the class interval. The n numbers 25 and 29 are the class limits. The smallest number 25 is a lower class limit and the largest number 29 is the upper class limit. The term class and class intervals are often used interchangeably, although a class interval is actually a symbol for class. A class interval that theoretically has either no upper class limit or no lower class limit indicated is called an open class interval. For example, if we define the first class interval in the above table as up to 30 years, it will constitute an open class interval. Sixth point, class boundaries. When we deal with a continuous variable, all the data are recorded nearest to a certain unit. Let us consider the example given as follows. We have constructed the class interval starting from 25 years of age, and first class interval pertain to the ages ranging between 25 to 29 years. Similarly, the next class interval pertains to the ages ranging from 30 to 34 years, and so on. While deciding about the numbers of persons falling against each class interval, we'll record the age of every individual in the nearer number of years. Suppose age of an individual is 29 years and 9 months. Will he stand against the year 29 or the year 30? We may decide that the person aging less than 29.5 years will be considered aging 29, and person aging more than 29.5 years will be considered aging 30. These numbers indicated briefly by the exact numbers like 24.5, 29.5 and likewise are called as class boundaries or true class limits. The smaller number 24.5 is a lower class boundary and the larger number 29.5 is the upper class boundary. The seventh one, the size or width of class interval. The size or width of a class interval is the difference between the lower and the upper class boundaries and is also referred to as a class width, class size or class length. If all class intervals of a frequency distribution have equal widths, this common width is denoted by C, small c. In such case, C is equal to the difference between the two successive lower class limits or two successive upper class limits. For example, in table 1.1, the class interval is C is equal to 30 minus 25, which is equal to 35 minus 30, which is equal to 5. If we have to decide the class width of the class from the given data, it will depend on the number of classes we want to construct. The class width can be calculated as range divided by the number of classes. Now the eighth one, class mark. The class mark is the midpoint of the class interval and is obtained by adding the lower and the upper class limits and dividing by 2. Thus, the class mark of the interval 25 minus 30 is 25 plus 30 divided by 2, which is equal to 27.5. The class mark is also called as class midpoint. For purposes of further mathematical analysis, all observations belonging to a given class interval are assumed to coincide with the class mark. Thus, all persons in the class interval 25 to 30 years are considered to be 27.5 years of age. In the construction of frequency tables, it is essential that there be clear definition of classes, so that there may be no uncertainty as to their range and no question as to precise class in which a given class falls. Following are the various methods of constructing class intervals, any of which can be opted according to the data available and the purpose of constructing the distribution. First one, exclusive method. In this method, the upper limit of one class would be the lower limits of the next class. That is, the class limits of two class intervals overlaps each other. So we have a table 1.2 over here. The value of 10 would fall in the first or in the second class. It will fall in the second class because the upper limit of the first class is exclusive of the value 10. These intervals are termed as exclusive class intervals because upper limit of such intervals excludes its extreme value. Although constructing these intervals lead to a kind of ambiguity, still they are most commonly used because they facilitate further computations. Second one, inclusive method. So table 1.2 can also be presented in the form of table 1.3 as given. In the above table, the given class intervals includes the values falling against its lower as well as upper class limits. In this way, the ambiguity of the above table 1.2 can be removed. Now let's come to the third one, open-end class intervals. A class which does not give the upper and the lower limits but instead is stated as more than or less than a specified limit is called an open class or open-ended interval. So we have a table 1.4 which gives us the age distribution of the merchant shipping vessels in the year 2000. Let's come to the fourth one, class intervals with cumulative frequencies. When frequencies are cumulated, the measurements of class intervals are also cumulated. Frequency may be cumulated either from the top or from the bottom. If the upper limit is used, it is preceded by the word below or less than, and if the lower limit is used, the word above or more than precedes. Before treating such data statistically, it is necessary to convert them into usual class intervals and individual frequencies. Table 1.5a gives us the class frequencies cumulated from top, Table 1.5b gives us the class frequencies cumulated from bottom. The above statistical data may be converted into usual type of class intervals. And individual class frequencies can be presented as follows. Table 1.6 shows this. First one, individual series. In this series, items are observed individually and are listed as individual cases. They may be placed in ascending order, descending order, or no order. Table 1.7 gives us a distribution of yearly income of a family. Second one, discrete series. In this series, when items are analyzed in groups showing definite breaks from one point to another and they're exactly measurable, they form a discrete series. Discrete or discontinuous variable is distinct and separate. That is, the values differ from each other by finite amounts. There will be gaps between one value and the next. For example, a man cannot have 1.5 children. He can either have 1 or 2 children, or likewise. There's only certain integral results are possible here. So here's a table which gives a distribution of vehicles owned by 10 families. Now the third one is continuous series. In this series, when items are distributed in groups or classes because they are not exactly measurable, they form a continuous series. A series is said to be continuous when it passes from one value to the next by indefinitely small gradations. Thus, the variable can be theoretically measured to any desired degree of precision. The degree of precision is purely the result of the accuracy of the measuring instruments. So table 1.9 gives us a distribution of monthly income of members of a club. A frequency distribution can be presented graphically in any of the following ways. First one, histogram. It is the graph that represents the class frequencies in the frequency distribution by vertical adjacent rectangles. While constructing histogram, the class intervals are taken on the x-axis and the frequencies depending on them on the x-axis, and y-axis represent the frequencies of each class, which constitutes the height of its rectangle. Each class is presented by a distance on the scale that is proportional to its class interval. The distance for each rectangle on x-axis shall remain the same in case the class intervals are uniform throughout. If they are different, the width of the rectangles shall also vary. Let's see the constructing of histogram when class intervals are equal. So here is an example for that. Example 1. Draw the histogram for the following data. So we have seen in the solution we are constructing the histogram. Constructing of histogram when class intervals are unequal. So we have an example over here, example number 2. It represents the following data by means of a histogram. So we have the solution to this as Now the second one, frequency polygon. A frequency polygon is a graph of frequency distribution. It has more than 4 sides. Polygon literally means mini angles. There are 2 ways in which frequency polygon may be constructed. First one, we may draw a histogram of the given data and then join by straight lines the midpoints of the upper horizontal side of each rectangle with the adjacent ones. The figure which is formed, that is called the frequency polygon. Now, second point, another method of constructing frequency polygon is to take the midpoints of various class intervals and then plot the frequency corresponding to each point, and to join all these points by straight lines. Frequency polygon has an advantage over the histogram. The frequency polygons of several distributions may be plotted on the same axis, thereby making certain comparisons possible, whereas histograms cannot be usefully employed in the same way. To compare histograms, we must have a separate graph for each. Because of this limitation for purposes of making a graphic comparison of the distribution, frequency polygons are preferred. Third one, smooth frequency curve. It can be drawn through the various points of the polygon. The curve drawn freehand in such a manner that the area included under the curve is approximately the same as that of the polygon. The object of the curve is to eliminate as far as possible all accidental variations that may be present in the data. For drawing this curve, firstly we draw the polygon and then smooth it out. The area under the curve should represent the total number of frequencies in the entire distribution. The following points should be kept in mind while smoothing frequency graph. The first point is, only frequency distribution based on samples should be smoothed. Second one, only continuous series should be smoothed. Third one, the total area under the curve should be equal to the area under the original histogram or polygon. Now let's come to an example here, example 3. Draw a histogram, frequency polygon and frequency curve representing the following figure. So we have a solution to this. Fourth one is ogives or cumulative frequency curves. It is the vertical axis cumulative frequency or relative cumulative frequency. The horizontal axis is the class boundaries. The graph always starts at 0 at the lowest class boundary and will end up at the total frequency. Sometimes one need to know the answers to questions like how many workers of a factory earn less than rupees 1000 per month, or how many workers earn more than rupees 1500 per month. To answer these questions, it is necessary to add the frequencies. When frequencies are added, they are called cumulative frequencies. These frequencies are then listed in a table called cumulative frequency table. The graph of such a distribution is called as a cumulative frequency curve or an ogive. There are two methods of constructing ogive. First one, less than method. In this method, we start with the upper limits of the classes and go on adding the frequencies. When these frequencies are plotted, we get a rising curve. Second method, more than method. In this method, we start with the lower limits of the classes, and from the total frequencies, we subtract the frequency of each class. When these frequencies are plotted, we get a declining curve. Now let's see an example 4. Draw a percentile curve for the following distribution of marks obtained by 700 students in an examination. Find from the graph, the first one, the marks at the 20th percentile, and the second one, the percentile equivalent to 65 marks. So the solution to this: a percentile curve is a cumulative percentage curve. Hence, for drawing such a curve, 3 steps are required. First one, find the cumulative frequency of the given data by the less than method. Second one, convert these cumulative frequencies into percentages of the total. Third one, take these percentages on the y-axis and variables on x-axis and plot the various points and join them by straight lines. The curve so drawn is known as the percentile curve. So we have this table. Percentile curve. Now example number 5. Draw a histogram and frequency polygon to present the following data. Solution: we'll take the various classes as 999.5 to 1499.5, 1499.5 to 1999.5, and etc. So let's quickly summarize what we have learned in today's session. We have learned today the introduction of frequency distribution, various terms used under frequency distribution, kinds of frequency distributions, their uses and various types of graphs of frequency distribution, and also we have gone through the different methods of constructing class intervals. So that brings us to the end of today's episode. We are ending here with the second part of collection and classification of data, and we'll see you again discussing about our next topics on more wide variety. Have a nice time. Thank you.